Okay, this is lecture 3 in cryptography. And the beginning part of the course, what we're doing now in chapter 1, is some basic elementary arithmetic, elementary number theory, which is the basis of all cryptographic methods. And what I had stated yesterday was the theorem. It's 120 in Hofstein's book, which is FTA, which stands for Fundamental Theorem of Arithmetic. And this says that every number, every positive integer, is a product of primes. Or if we don't want to worry about the number 1, which is the empty product, a product of no primes, that a be an integer greater than or equal to 2, then you can factor a as a product of prime powers, p1 to the e1, p2 to the e2, up to, let's say, p sub r to the e sub r, where p1, p2, up to p sub r are distinct prime numbers, and the exponents are all at least 1. And this representation is unique unique up to the order of the factors. So for example, 6 is 2 times 3. It's also 3 times 2. These are exponents 1. So other than the order in which you write down the prime numbers 2 and 3, this is a unique representation of 6 as a product of primes. And the proof is divided into 2 parts. There is existence of a prime factorization. It's factoring this number into a product of primes. And there is the uniqueness of the prime factorization. Let me add one important remark. Factoring a positive integer into a product of primes is unbelievably hard. Now, you might not think it's so hard, because, for example, you could go to Maple and ask Maple to factor a number for you. Let me see if I can share the screen with Maple. So I hope you see this Maple screen. And if you took calculus at Lehman, you should have or might have learned Maple. In any case, it's a basic computer algebra program, extremely powerful, which you can get for free from CUNY if you're a student. And there's a command called ifactor. So if you put in a number like 6, whoops, we got the parentheses. I factor 6 is 2 times 3. That's not very challenging. Here's a number I just typed in at random. This interesting number is a product of 3 primes, 3, 41, and this. And you might remember or know that in Maple, there's a command which tells you if a number is prime or not. It says is prime is the command. And oops, what happened to that? This asks the question, is this number prime? Or sorry, it's the statement. This number is prime, true or false? And it's true, that guy is prime. And if you're suspicious, let's put in a number which is obviously not prime. I'll change the 9 to an 8. Is this prime? That's false. Of course, it has to be false because it's even. But suppose I make an even bigger number. I'm just typing in some random digits. Okay. I have no idea even how to pronounce that number, but, oh. Well, of course it's false. It ends in 2. Let me add a number 3. Let's see. Is prime. Huh. Well, if it's not prime, let me try to factor it. So this very big number is a product of these primes. 7, 11, 83, 107. This guy is 12,587,501. This is thousands, millions, billions, trillions, quadrillions. In any case, you might think, look at that, Maple factored this huge number in probably in less than a second. So you might think a computer can factor big numbers. Well, you might think of this number as big. I mean, the wealth of the world is less than this number. The population of the world is an infinitesimal, almost fraction of this number. But as numbers go, this is not so big. You can have a number with 1,000 digits or 100,000 digits. And if you take such a number, it is simply the unfortunate, oops, I needed to stop share. Yeah. So you might think if you play with Maple, that factoring primes is easy. You just use the command ifactor. But for big numbers, thousands and thousands of digits, there is in fact no computer in existence that can factor the number. No one can prove that factoring is hard. This is a major unsolved problem in computer science, that you cannot write a computer program to factor a large number in what might be called polynomial time. And it is definitely true that if one could construct a quantum computer, what actually initiated a lot of the interest in quantum computing was an algorithm that would allow a quantum computer to factor an integer in a relatively short time. So one knows that if you could build a quantum computer, you could factor integers, but no one has yet learned how to build a quantum computer. Let me ask you, if you're not muted, to unmute yourself, because there's background noise, which is not good. Okay. So the fundamental theorem of arithmetic says that every number is a product of primes, but the computer problem, I'm sorry, whoever is speaking, you can speak, but you have to unmute yourself.
Andrea, your speaker.
Sorry, you have a question?
No.
All right. So factoring a positive integer into a product of primes is hard, but the fundamental theorem of arithmetic says that a factorization always exists. Right? This is, in fact, probably the biggest unsolved problem in theoretical computer science. So how do we know that every number is a product of primes? So first of all, take the number 2. Well, that's a product of primes. It's a product of 1 prime. 3 is a product of 1 prime. 4 is 2 squared. 5 is 5. 6 is 2 times 3, and so forth. So you can check in the beginning, and I want to prove by induction on A that every integer A greater than or equal to 2 is a product of primes. So assume we've proved this for all integers less than some number A. So we have to consider A. There are 2 cases. In the first case, A is prime. And then we're done. A is equal to A. It's a prime number. In case 2, A is not prime. A number which is not prime is called composite. In that case, A factors. A equals B times C, where B and C are both numbers strictly smaller than A and bigger than 1. But by the induction hypothesis, what is the induction hypothesis? That every number less than A is a product of primes. B is less than A. So B is some product of primes. And C is less than A. So C is also some product of primes. I'll write them Q1, F1, Q2, F2, up to Q sub L, F sub L. So B and C are both product of primes, but A is B times C, which is P1 to the E1, P2 to the E2, Pk to the E sub K, Q1 to the F1 up to QL to the F sub L. And we can combine these if one of the P's equals one of the Q's, like if P1 equaled Q1, this would be P1 to the E1 plus F1, and so forth. But in any case, A is a product of primes, so we're done. So the proof that every integer greater than 1 is a product of powers of distinct primes is this inductive proof. Right? This is the easy half of the fundamental theorem of arithmetic. What is harder is to prove uniqueness. And so to prove uniqueness, we do it as follows. Suppose A is some product of primes. I'll just write out the primes. They're not distinct now, just some product of, let's say, S primes. But also, there's another way to write A as a product of primes, Q1 up to Q sub T, where the Pi and the Qj's are prime numbers. And S doesn't have to equal T. I'm saying, suppose I can write A as a product of primes in one way and as a product of primes in a second way. I must show that the number of primes is the same, S equals T. And in fact, after rearranging, if necessary, P1 equals Q1, P2 equals Q2, and so forth, PS equals Q sub S. They're exactly the same primes, right? That's what uniqueness means. But recall Euclid's lemma. Euclid's lemma says that if P is prime and P divides the product of two integers, then either P divides A or P divides B. So this is Euclid's lemma. If a prime divides the product of two integers, it divides one of the factors. And then this was extended as follows. If a prime P divides some product of any number of factors, then P divides one of the factors. So if a prime P divides a product, it divides one of the factors. And note, this is only true for primes. For example, 4 divides 2 times 2 times 3, but 4 does not divide 2 or 3. Or if you want a slightly different example, 4 divides 6 times 8, 6 times 10, but 4 does not divide 6 or 10. So the reason is that 4 is not a prime. Right? The statement about divisibility is only true for prime numbers. Right? It has to be a prime. But now let's use Euclid's lemma to prove uniqueness. So suppose A is P1 up to P sub S, a product of primes, and there's another product of primes, Q1 up to Q sub T. So P1 divides A. Because PA is P1 times P2 up to P sub S. P1 times P2 up to PS is A. P1 divides A. So P1 divides Q1 up to Q sub T, this product. But P1 is prime. So P1 has to divide one of these factors. P1 divides Qj for some J. But Qj is a prime. The only factors of a prime are 1 in itself. So P1 is a factor of Qj. P1 is not 1, so it has to equal Qj. So P1 equals Q sub J. So renumbering, we can assume that, in fact, P1 equals Q1. But if P1 equals Q1, I can cancel. I can divide. So I get A over P1, which is an integer, that's P2 up to PS, is Q2 up to Q sub T. And I can continue in exactly the same way. P2 divides this product, so it divides one of the factors. So renumbering, we can assume that it divides the first, and we can cancel the P2. And we continue until we run out of primes. And finally, we get that the primes here are the primes here, and we're done. Or we could say we're doing this by induction. It's supposed to be true for every number less than A. So take A, take the prime P1, it's equal to some Q1. So A over P1 is this product. A over P1 is less than A because I'm dividing A by a number at least 2. So in this factorization by the inductive hypothesis, which is that every number strictly less than A is a product of primes uniquely, these primes equals these primes up to some rearrangement. And that's the whole proof. So this is not only one of the most important theorems in number theory and in cryptography, but it's something which is likely to appear on a midterm or a final because really it is a fundamental result in mathematics, and you should know it. Okay. We already defined congruence classes, Z mod MZ, which is the set which we represent by the non-negative integers from 0 up to m minus 1. And we can think of these as congruence classes. So for example, 2 means the set of integers A that are congruent to 2 modulo m. And in this set, which is a finite set, we define addition modulo m. A plus B equals C in Z mod MZ if A plus B is congruent to C mod M. So if we're looking at, for example, Z mod 12Z, which is the numbers 0 up to 11, 8 plus 9 is equal to 5, because 8 plus 9 is congruent to 5 mod 12. That is 17 is congruent to 5 mod 12, and 17 minus 5 is 12. And similarly, 8 times 9 is 0, because in this 8 times 9, which is 72, is congruent to 0 mod 12. So this is the arithmetic in the congruence classes. And the most important case for us is when this modulus m is a prime. We're looking at Z mod PZ, where P is a prime number. So this consists of the number 0, 1, 2 up to P minus 1. And this set of numbers has the following property. You can not only add, subtract, and multiply, but you can divide by anything non-zero. So if A is not 0 in this set, then there exists a B in the set such that AB equals 1. In other words, B is like 1 over A. And why is that? This is equivalent to saying that for all A not congruent to 0 mod P, there exists an integer B such that AB is congruent to 1 mod P. And we prove that this is the case. Let me show you another simple proof. So suppose AX is congruent to AY mod P for some integers X and Y. Then AX minus AY is a multiple of P. AX minus A, to say two numbers are congruent mod P means their difference is divisible by P. So this is A times X minus Y equals P. So P divides X minus Y. So, excuse me 1 minute, I'll be right back. So suppose AX is congruent to AY mod P. That means the difference is divisible by P, which A times X minus Y is P. So if P divides A times X minus Y, that means by Euclid's lemma, P divides one of these factors. P divides A, or P divides X minus Y. But this says A is not congruent to 0 mod P. So this doesn't happen, so this has to happen. P divides X minus Y, so X is congruent to Y mod P, which is a very interesting result for us, because this says that AX congruent to AY mod P if and only if x is congruent to y mod p. But the numbers 0, 1, 2 up to p minus 1 are not congruent modulo p. So if I take a times 0 mod p, a times 1 mod p, a times 2 mod p, all the way up to a times p minus 1 mod p, these are distinct mod p. But there are p of them. I have p numbers distinct mod p. But these are the only numbers that are distinct mod p. So this a times 0, a1, a2, this is just some rearrangement of the numbers from 0 up to p minus 1. And that must imply that there exists x such that ax is congruent to 1 mod p. One of these numbers has to be 1. Right. So that tells us that in the integers mod p, if a is not congruent to 0 mod p, then a is invertible. Invertible means ab is congruent to 1 mod p for some b. And we can think of this b as being like 1 over a. So if you wanted to divide in z mod pz, if you wanted to take a number r and divide it by a, that's just going to be equal to r times 1 over a, or r times b mod p. So that says z mod pz is what we call a field. A field in algebra is a set of numbers that you can add, subtract, multiply, and divide. Right? So z mod pz is a field, just as the real numbers, the complex numbers, the rational numbers, these are also fields. Right? And of course, the simplest field is if you take p equal 2, z mod 2z just consists of 0 and 1. And this gives you the binary arithmetic that is basic in computer science. Okay. Now, very often in applications of finite fields in cryptography, we have to take high powers of elements. So z mod pz, this field, we often write as f sub p. This is the unique field with p elements, where p is a prime. And we already saw that there is a very efficient way to raise numbers to powers by taking the power and writing it as in binaries, a sum of powers of 2. Things are even simpler if you're taking powers in this finite field. And the basis of this is a theorem, which is sometimes called Fermat's little theorem. He had a lot of theorems, but this one is particularly important. It says the following: let P be a prime and A an integer. If you take A to the power P minus 1, this is congruent to 1 mod P if A is not equal to 0 mod P. And A to the P minus 1 is, of course, 0 mod P. If A is congruent to 0, A is congruent to 0 mod P. The second part is sort of trivial. If A is 0, 0 times 0 is 0. No matter how many times you multiply 0 by itself, you'll only get 0. So if A is 0 mod P, every power of 0 mod P is 0 mod P. If A is not 0 mod P, the powers of A are never 0 mod P. The amazing fact is that A to the power P minus 1 is always 1 mod P. And let's just actually look at some examples of this. Suppose P is equal to 2. Well, of course, if A is not 0 mod 2, then A is equal to 1. That's all it can be. And 1 to any power. So 1 to the P minus 1 to the 1 is just 1 mod P. That's not too exciting. In fact, 1 to any power is always 1 mod P. Suppose I take P equal 3. The only number, the numbers that are not 0 mod 3 are 1 and 2. So 1 to the any power is 1, but 2 squared is 4, and 4 is congruent to 1 mod 3, because 4 minus 1 is 3. Suppose I take the next prime, which is 5. And in that case, P minus 1 is 4. So 1 to the 4th power is, of course, 1 mod 3. What is 2 to the 4th power? 2, 4, 8, 16, sorry, mod 5. 16 is congruent to 1 mod 5, because 16 minus 1 is 15. What is 3 to the 4th? 3, 9, 27, 81. 81 is congruent to 1 mod 5. 81 minus 1 is 80, is 5 times 16. What about 4 to the 4th? Let's see, what is 4 to the 4th? 4, 16, 64, 256 is congruent to 1 mod 5. Because 256 minus 1 is 255. So for P equal 5, every non-zero number raised to the 4th power is congruent to 1. Huh. This is kind of fun. Let's try another example. This one might be a little more computationally rigorous. Suppose I take P equals 7. In that case, P minus 1 is 6. 1 to the 6th, of course, is 1 mod 7. 2 to the 6th. 2 to the 6th is 64. 64 minus 1 is 63. 63 is divisible by 7. So 64 is congruent to 1 mod 7. What about 3 to the 6th? Three to the 6th is 729. So 3 to the 6th minus 1, 729 minus 1 is 728. Well, of course, you can actually see this is divisible by 7. This is 7 times 104. So 3 to the 6th is congruent to 1 mod 7. What about 4 to the 6th? 4 to the 6th is 2 to the 12th. Let's say 2 to the 10th is 1024. Multiply that by 4, you get 4096. 4096 minus 1 is 4095. Is this divisible by 7? Yes, miraculously, this is 7 times 585. So 4 to the 6 is congruent to 1 mod 7. What about 5 to the 6th? So 5 to the 6th power is 15,625. Subtract 1, that's 15,624. Divide that by 7. Lo and behold, it divides evenly. It's 7 times 2,232. So 5 to the 6th is congruent to 1 mod 7. Of course, we could have done this another way. 5 is the same as minus 2 mod 7. So 5 to the 6th is like minus 2 to the 6th, which is minus 1 to the 6th, 2 to the 6th. Minus 1 to the 6th is 1. This is 2 to the 6th. And we already saw that 2 to the 6th is congruent to 1 mod 7. And similarly, 6 is congruent to minus 1 mod 7. So 6 to the 6th is congruent to minus 1 to the 6th. Minus 1 to an even power is always 1 mod 7. So I just proved, I just confirmed Fermat's little theorem for the primes 2, 3, 4, 2, 3, 5, and 7. That's kind of nice. But we want to prove that it's true for all primes. So let's see. So I'm going to give 2 proofs. So the first proof is will only make sense if you've taken Math 314, which is algebra. Because in that case, there's a very, very short proof. And then I'll give a second proof, which...
The professor, can you hear me?
Yes.
Yeah, I have a question.
Go ahead.
Yeah, where you got the negative congruent to negative?
-1?
Now on the first one, 5 equal -2.
Yes. Where did I get that?
Yeah, top one.
This.
Top, yes.
Okay, well, 5 plus 2 is what?
7.
Thank you. So 5 minus -2 is what?
7.
So 5 is congruent to -2 mod 7.
Okay, got it.
Okay.
Thank you.
So Fermat's little theorem. If A and P are relatively prime, if the GCD of A and P is 1, then A to the power P minus 1 is congruent to 1 mod P. Right? So proof number 1, using algebra, which is Math 314. So Z mod PC star, so this is the non-zero elements in this field. 1, 2, 3, up to P minus 1. This is a multiplicative group. Because you can multiply any 2 of these numbers and you get one of the numbers in the group. And every number has an inverse and so forth. It's a multiplicative group. And how many elements are in the group? P minus 1. So by Lagrange's theorem in algebra, which says that if A is in a group G of order n, then A to the n is the identity, right? So in our case, if we have A and Z mod PZ star, the non-zero elements, this group has order P minus 1, so A to the P minus 1 is equal to 1. Or in the group, or A to the P minus 1 is congruent to 1 mod P. So only if you know algebra does this make sense, but if you do know algebra, it's a very nice application of Lagrange's theorem. But proof 2 won't use Lagrange's theorem. It should be completely direct and elementary. So we already showed a few moments ago, we showed that if A and P are relatively prime, or the same thing, A is not equal to 0 in Z mod PZ, which is this finite field with P elements, then the elements 1 times A, 2 times A, 3 times A, and so forth, up to P minus 1 times A are distinct. So now we do something clever. Multiply all these numbers together. So if I take 1 times A, 2 times A, 3 times A, up to P minus 1 times A, on the one hand, what is this equal to? I have A occurring P minus 1 times, and then 1 times 2 times 3, and so forth, what we call P minus 1 factorial, the product of all the integers up to P minus 1. But on the other hand, these numbers are distinct. So these numbers are just the numbers from 1 to P minus 1 in some order. So again, working in this finite field, this is the same as the product of the first P minus 1 integers, P minus 1 factorial. So what we have is P minus 1 factorial is A to the P minus 1 times P minus 1 factorial. But this number, P minus 1 factorial, is not 0. It's not divisible by P. It's the product of the integers 1 up to P minus 1. None of them is P. So we can cancel it. And when we cancel, we get 1 equals A to the P minus 1 in Z mod PZ, or in the integers, A to the P minus 1 is congruent to 1 mod P. So that is the proof of Fermat's little theorem. And whether you're taking this as a math class or a computer science class, this is something you need to work through and understand. The text gives a kind of ridiculous example of this. So if I take the number 154,858,63, 15,485,863, this is prime. So if I subtract 1, I get 1548562. I raise 2 to that power. Well, I don't want to calculate it. I just want to know what this is congruent to modulo this number, 15,485, 863, and this is congruent to 1 mod p. One other fact is the following. A to the p minus 1 is congruent to 1 mod p. If I multiply by A inverse, which is the same as saying that A, p minus 1 minus 1, A to the p minus 2 is congruent to A inverse mod p. So A inverse is always A to the p minus 2 mod p, which is sometimes a useful fact.
So, Professor,
Yes.
is there any rule like if the power is also prime and mod is also prime, then it will not congruent to 1?
Well, the power, let me find an example. Suppose I take p equal to 7.
Mm-hmm.
So this says that if a to the 6th is congruent to 1 mod 7 for a
Mm-hmm.
equal to 1, 2, 3, 4, 5, and 6. Okay.
Mm-hmm.
However, if I take a equal to 2,
Mm-hmm.
of course, 2 to the 6 is congruent to 1 mod 7,
Mm-hmm.
but also 2 cubed is congruent to 1 mod 7. So there's a smaller power of 2, which is congruent to 1 mod 7. But I don't think that's what you're asking. Repeat your question again.
That's in case of 3, like suppose 3 exponent 3 mod 7.
So 3 cubed is 27, is congruent to 6 mod 7. It's not congruent to 1 mod 7.
Yeah, that was my question. Then it will not be 1, right?
No, not necessarily.
Oh,
It could
okay.
be, like here, 2 cubed is 1 mod 7, but
Mm-hmm.
3 cubed is not 1 mod 7.
Other than 2, all like 4 cube also not work? Other
Well,
than 2?
I don't understand what you mean by not work. If you take 4 cubed is 64, is congruent to 1 mod 7,
Okay.
right?
Mm-hmm.
5 cubed is 125. If you divide 125 by 7, that goes in,
It's not
you get 6 mod 7.
like that. That was my question. Like if it is 2, 4, that's working, but if it is 3, 5, 7 to the cube, that will not be
7 cubed is 0. But it
right.
depends on the particular prime. For example, if I take p equal to 11,
Mm-hmm.
2 to the 10th is congruent to 1 mod 11
Mm-hmm.
by Fermat's theorem.
Mm-hmm.
If I take, let's say, 2 to the 5th, 2 to the 5th is 32. That's congruent to 10 mod 11. It's not congruent to 1 mod 11.
Mm-hmm.
Right?
Okay.
But it varies with the prime. It's very hard to, in fact, it's a famous unsolved problem for over 1,000 years.
Mm-hmm.
Suppose you have a prime p, right?
Mm-hmm.
We know that 2 to the p minus 1 is congruent to 1 mod p.
Mm-hmm.
And the question is, does there exist a number k less than p minus 1,
Mm-hmm.
such that 2 to the k is congruent to 1 mod p?
Mm-hmm.
And the answer is, there's no rule to figure out the answer to this question yet. For example, maybe this happens only finitely many times. No one knows.
Okay. Not necessarily that applies to everything.
Correct.
Okay. Thank you so much.
Okay. Let's see. This is page 9. So here's just an interesting example that you find in the text. This is example 1.28 on page 32. Take a number m, which is 15,485,207. And if you compute 2 to the power m minus 1, right, which if you use the fast powering algorithm, you can calculate this. This is 2 the power of 15,485,206. This is congruent to 4,136,685 modulo 15,485,207. In other words, this is not congruent to 1 modulo this number, which means m is not prime. So this is not necessarily the best way to show that this integer is not a prime. But the fact, if I take this number m and I raise 2 to the m minus 1, and I get a number different from 1, then that absolutely positively tells me that this number is composite. Actually, I'm sort of curious. Let me just go back to Maple for a second. Share screen. Let me do that. So if I let m be this number, 15,485,207, and I want to factor it, so the command to factor an integer in Maple is ifactor. So ifactor m. So this number is a product of these two 4-digit primes. That's kind of interesting. Okay. Let's see what else I need to talk about. Oh, okay. So there's one more theorem which I'm going to state, but I'm not going to prove, because that requires a bit more algebra and number theory than I need to require here. But first I'll prove a very nice theorem. This is also something which is you would have seen in an algebra class perhaps, but this is proposition 129 in our text. We have a prime number p, and a, an integer, not divisible by p. So a is not congruent to 0 mod p. That's another way of saying that p does not divide a. So we know that a to the p minus 1 is congruent to 1 mod p. So that n be the smallest positive integer such that a to the n is congruent to 1 mod p, then n divides p minus 1. So we just saw an example of that. When I take a equal 2 and p equals 7, and p minus 1 therefore is 6, we know that 2 to the 6 is congruent to 1 mod 7. 2 to the first power is 2. It's not 1 mod 7. 2 squared is 4, which is also not 1 mod 7. 2 cubed is 8, which is 1 mod 7. So the smallest power of 2 that's congruent to 1 mod 7 is 3. And 3 divides 6. The smallest power of 2 that is congruent to 1 mod 7 divides 7 minus 1. So this is not an accident. This is a general phenomenon. You take a prime number p, you take an integer a that's not 0 mod p, then the smallest power of a that is equal to 1 mod p must divide p minus 1. Right? And there's a very pretty proof of that, which is the following. Let me just, okay. Actually, I'm going to state this in, so I want to follow the text. I want to state this in a slightly more general way. So it'll be the following. And this is proposition 129. So P is a prime. A is not divisible by P. So A is not congruent to 0 mod P. And let K be the smallest positive integer such that a to the k is congruent to 1 mod p. So we call this, so this is just sort of a definition. K is called the order of a modulo p. If n is any integer such that a to the n is congruent to 1 mod p, then k divides n. So in particular, a to the p minus 1 is congruent to 1 mod p. So k divides p minus 1. And the proof is very simple. Do long division. N, if you divide it by k, has a quotient q and a remainder r. And the remainder is between 0 and k minus 1. So if I take a to the n, that's the same as a to the kq plus r. That's a to the kq times a to the r. Just by rules for exponents. A to the kq is a to the k to the q times a to the r. But a to the k is 1 mod p. So this is congruent to 1 to the q times a to the r mod p. 1 to any power is 1, so this is just a to the r mod p. And a to the n is 1 mod p. Right? A to the n is 1. So what I have is that a to the r is congruent to 1 mod p, and r is between 0 and k minus 1, because r is the remainder you get when you divide n by k. But k is the smallest positive power of a, which is 1 mod p. And r is less than k. It's at most k minus 1. So r cannot be positive. So r has to equal 0. Because k is the smallest positive integer, such that a to the k is 1 mod p. So n is equal to k times q. My remainder is 0. That is k divides n. And that is a complete and very beautiful proof of this result. Okay. Now the theorem I'm not going to prove, but the proof really is a little bit difficult, is the theorem about what are called primitive roots. So we say that an integer a is a primitive root of p, or of fp, primitive root of fp, if, let's let me call it g, an integer g is a primitive root of fp if, let me write it in several ways, fp star, which is the non-zero elements of fp, are exactly the powers of g. 1g, g squared, g cubed, up to g to the p minus 2. It's p minus 2 because altogether there are p minus 1 elements in this set. Or equivalently, if, so that's one definition, or equivalently, if a is not congruent to 0 mod p, means a is congruent to g to the k mod p for some k. That is, if the powers of g give you every number which is not 0 mod p, then g is called a primitive root. And the theorem says that primitive roots exist. It's not obvious that primitive roots exist. If I have a prime p, there is no reason a priori to think that there's some number somewhere in the universe such that the powers of that number give you every integer relatively prime to p. But it's true. If you have a primitive root, note that if g is a primitive root, then these numbers are distinct. So g to the k is not 1 mod p, or k going from 0 up to p minus 2. But of course, by Fermat's little theorem, g to the p minus 1 is congruent to 1 mod p. So g has order p minus 1 mod p, that is, and conversely. So the order of an element mod p is the smallest power of that element, that's 1 mod p. And an integer g is a primitive root mod p if and only if it has order p minus 1. And as a general fact, finding primitive roots is a very hard problem. And I'm using hard in two senses. It's hard given a prime to find a primitive root in any theoretical way. In fact, it's not possible, it's not known. And using a computer is hard. There's no efficient computer algorithm, computer program that can find a primitive root for you. So let's look at an example. Suppose I take the field F11. So this is the congruence classes, mod 11 from 1 to 10. And so F11 star, the non-zero classes, are just the integers from 1 to 10. I claim 2 is a primitive root. So let's do the calculation. 2 to the front is 2. 2 squared is 4. 2 cubed, I'm doing this everything mod 11, 2 cubed is 8. 2 to the 4th is 16, which is 5 mod 11. 2 to the 5th is 32, which is 10 mod 11. 2 to the 6th, well, actually, is 2 times 2 to the 5th, so that's 20, which is 9 mod 11. 2 to the 7th is 2 times 2 to the 6th, which is 2 times 9, which is 18, which is 7 mod 11. 2 to the 8th is 2 times 2 to the 7th, which is 2 times 7, which is 14, which is 3 mod 11. 2 to the 9th is 2 times 3, which is 6 mod 11. 2/10 is 2 times 6, which is 12, which is 1 mod 11, which is what we expect. So if I look at, and 2 to the 0, I should have said is 1. So what are the congruence classes that I get mod 11? I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have them all. So 2 is a primitive root, mod 11. Let's take another prime, say p equals 17. So 2 to the 16 is congruent to 1, mod 17, by Fermat's little theorem. Is 2 a primitive root mod 17? Well, let's start to calculate the powers. 2 to the 0 is congruent to 1, of course. 2 to the first power is 2. 2 squared is 4. 2 cubed is 8. 2 to the 4th is 16. 2 to the 5th is 32. Mod 17, that's the same as 15, mod 17. 2 to the 6th is 2 times 15, 2 times 2 to the 5th, which is 2 times 15, which is 30, which is 13 mod 17. 2 to the 7th is 2 times 2 to the 6th, that's 2 times 13, which is 26, which mod 17 is 9. 2 to the 8th is 2 times 2 to the 7th, which is 2 times 9, which is 18, which is 1 mod 17. So this is the critical fact. 2 to the 8th is 1 mod 17. So as I start taking the powers of 2, I get 1, 2, 4, 8, 16, 15, 13, 9, and then I'm back to 1. So 2 to the 9th is 2 times 2 to the 8th. This is just, again, 2 mod 17. And as I continue to take powers of 2, I'm just going to cycle. I'll go from 1 to 2 to 4 to 8 to 16 to 15 to 13 to 9, and then back to 1. So I'll never get 3 or 5 or half of the congruence classes. So 2 is not a primitive root mod 17. Okay. All right, well, that is, I believe, at least for a long time in the course, the number theory we need. I didn't prove the theorem that every prime has a primitive root. That's very hard to prove. What we know is that, for example, 2 is sometimes a primitive root for some primes, but not for all primes. And in general, as I say, to find a primitive root given a prime is extremely difficult computationally. And you would get rich and famous if you could figure out a way to do this, because it has a lot of practical importance. Okay. That is it for today then. I will, yeah. See you
Thank you,
again
Professor.
at same time, 11 o'clock tomorrow. Also, today and tomorrow, if you have questions, I'm going to have a Zoom sort of office hour problem session at 7 o'clock tonight and also at 7 o'clock tomorrow. But keep in mind, at the start of every class at 11, I ask for questions, and you can ask me anything that you need to ask or want to ask at that time. Okay, that's it for today.
Have a good one, Professor. Stay safe.
Thank you.
Thank you. Bye-bye.
No problem.